Inversion of temperature is another of the very important causes for many atmospheric phenomena. If you look at the way the atmosphere is structured and some of the reasons why the troposphere is the weather layer and why all phenomena are trapped in the tropospheric layer of the atmosphere, the reason is temperature inversion. And in recent times, whether we talk about pollution, smog, and even deep fogs that get trapped and the pollutants getting trapped in the low atmosphere is again linked to atmospheric inversion. Now, atmospheric or temperature inversion is the reason why the atmosphere does not circulate very effectively. Why? Because inversion kind of traps the air in the lower layers or traps the layer within the inversion layers. So that was a quick introduction about this concept. Now let me explain this, how this happens and what are the fundamental reasons why inversion can take place. What we know about the troposphere is the troposphere has normal lapse rate, which implies as we go higher up from the surface of the earth, the temperatures progressively keep on decreasing. Of course, I'm talking in the context of the troposphere. So if I have the surface of the earth, we have the troposphere, we have the stratosphere, the mesosphere. In the troposphere, temperatures are consistently reducing. And the reason for this is the troposphere and the atmosphere is heated from below in this layer. So the surface is the warmest. As I go above, the energy absorbed by the layers progressively away from the surface is lesser. So at this height, the temperatures are less than the height at the surface. At this height, temperatures are lesser than the temperatures at this height, and so on. That's why if we plot the height versus the temperature graph, what we get is a line with a negative slope, which means at lower heights, the temperatures are higher. As the height increases, the temperature is lower. I think most of us know this, and a concept linked to this is a concept called as lapse rate or normal lapse rate, which for a steady state atmosphere is 6.4 or 6.5 degrees centigrade per kilometer. So I assume this is something we know. Now, what happens in inversion is this pattern of temperature falling with height inverts. Rather than the temperature falling with height, the temperature actually starts warming for some height. So we represent that in a curve which has a kink or a bend wherever we have inversion. So if it was the normal condition, the temperature, a height curve would have been a straight line like this. Because of inversion, maybe in this layer, the curve has now bent. So what I have is, for this layer, where the curve has changed, we call this as the inversion layer. And this layer essentially means as I go higher, temperatures are increasing. So for this height above the surface, temperature is this. Whereas for this height above the surface, temperature is this. So this temperature T1 is actually less than the temperature T2, at a higher height. So this is the layer of inversion where the pattern has now changed. Now this inversion can happen at any layer. It need not always be here. It can be for some other layers also. So we could have inversion at layers of upper troposphere. So temperatures fall and then again an increase of temperature like what we have in stratosphere, and the temperatures again start falling like what we have in the mesosphere. In fact, the stratosphere is also sometimes referred to as the inversion layer of the atmosphere. So this you understand as what is inversion and what does the inversion temperature curve look like. It has a different slope than the regular lapse rate curve. Now, what are the types of inversions and why do we have them? Okay, that's an important discussion. Now, broadly, we can divide the type of inversions under three heads. One is the radiation inversion. Second is the upper troposphere inversion, and this can be related to stratosphere like I mentioned here, or some other phenomena also referred to as subsidence mechanical inversion. And the third type is advection. As I hope all of us remember or recall, advection essentially means winds, or advection essentially means horizontal movements. Okay, so and advection, there are three different types of advection inversions. Let me take up one by one. The first is, what is radiation inversion? Essentially, if this is the ground and the temperature is supposed to fall with height, where the temperatures in the lower layer T1 is more than the temperatures at height T2. But what happens is, in conditions like severe winters of the high latitudes, or it could be the night time in the deserts, in the absence of clouds, in the absence of moisture, the surface can lose heat very rapidly. Land as it is has low specific heat. So the surface can lose heat very rapidly. Consequently, the surface becomes very cold. And in high latitudes, the surface can actually be below the freezing point. The surface being very cold, the air in contact with the surface and near the surface can also be very cold. So rather than having warm air here, we actually have a very cold air. Why? Because the land has lost heat very rapidly due to radiational losses. So rather than consistently falling temperature, we actually have fall of temperature for some height, and the lower layers, we actually have warming of the layers with height. We call this as radiation inversion. Okay, why? Because the land and the lower layers have cooled because of radiational losses. And I repeat, it's common for severe winters on the land, in the high latitudes, in the polar regions, and also in the tropical deserts. Why? Because in the absence of the clouds and moisture, the air can start losing heat very rapidly. The land can lose heat rapidly, and the air in contact with the land or near the land also becomes cold enough. So that's radiation inversion. Upper tropospheric inversion. So this I have mentioned as stratospheric inversion as one type. Basically, the stratosphere, okay, beyond 30 kilometers of the atmosphere, the stratosphere has ozone, say gases. It has ozone molecules, which are capable of absorbing the short wave ultraviolet radiations. So this layer can trap heat and become warm, whereas for the rest of the radiation, the troposphere is transparent to insolation. So the stratosphere gets warm and the troposphere relatively is cooler, hence we have the condition called as stratospheric inversion. Now another type of upper tropospheric inversion is also called as subsidence, which is one type of Alhamdulillah. Another type of upper tropospheric inversion is the subsidence type of mechanical inversion. Now we are referring to troposphere, but in the higher heights. In latitudes where we have high pressures, in latitudes where we have anticyclones, the air is actually sinking. So what we have is, this is the surface and this is the upper troposphere. And because of convergence here, the air starts sinking and I have got anticyclones or high pressure here. Now this sinking of air kind of adiabatically warms the air. Yes, the air can keep on sinking and even this layer can get warm. But this typical inversion happens again in the winters. It happens in the higher latitudes where the land is cold, but in the upper layers, because of sinking air, this part of air becomes a bit warmer. if you remember what I mean by adiabatic warming. So now relatively these layers are cooler. Even if the air sinks down and warms this layer continues to be cooler because the surface itself is cold. We're talking about winters in the mid latitudes and in the high latitudes. So this is the subsidence or mechanical type of inversion. Another type of upper tropospheric inversion, again mechanical, is the convective inversion. So and that's related to some bit of turbulence. Basically, this can happen in conditions of summers and land heating up. When the land is so hot, the air which is warm rapidly rises, and this warm air reaches the upper layers. So suddenly after some time, the upper layer has warmer air and the lower layers are relatively cooler than the upper air. That is an example of, again, mechanical, but we call that as turbulence inversion, which is happening in the upper part of the troposphere. So I've explained radiation and upper tropospheric inversion. The third type of inversion is advection inversion. In advection inversion, what we have is, we have some horizontal movement of air that creates this anomaly. So think of this condition where this is a surface where this should have been the lapse rate. But for whatever reason, if a cold air was to move in, so the lower layer now becomes cooler, the upper layer air becomes warmer. Or if a warm air happens to enter in the above layers, so the above layer now becomes warm, the lower layer is cooler. So essentially, this is a kind of horizontal movement that creates inversion. And the most common type of this is the frontal inversions. So we understand fronts. In fronts, the air masses, so we have a cold air pushing from below, the warm air forced to rise up. This is the cold sector, this is the warm sector, because of which the upper air now is relatively warmer, the lower air now is relatively cooler. So frontal inversion, this is again typical of the areas that have fronts, that have temperate cyclones. In fact, along the fronts and temperate cyclones, this is a very common phenomenon, the frontal inversion. Winds I have explained just now. Now let me explain the valley inversion. Now valley inversion is a consequence of what we otherwise know as mountain breeze and valley breeze. Now this is a phenomena, the inversion is a phenomena during the night times. What happens is, in the night times or late evenings, the mountain heights become cooler. If this was the mountain, in the evenings, the mountain heights become cooler because very rapid loss of radiation, and the surface becomes cooler, the air in contact becomes cooler, and this cold air is a heavy air. It's a very cold air, and this heavy air under its own weight slides down along the slopes, and the cold air accumulates along the valleys. This looks like a vertical movement, but this actually is not a vertical movement. It is a movement along the surface, and the surface is inclined. Please differentiate this. This is a surface, and this upward and downward motion of air is what's called as currents. Why? Because the movement is perpendicular to a surface, but along the slopes, the surface itself is inclined. So a movement along this surface will not be called as air currents. These are still winds. The current probably will be somewhere here. This probably is the air current where the air is rising or sinking under its own difference of temperature. But this is along the surface. So this is the surface of the mountain. The upper air is cooler because of radiational losses, and the cold air starts sinking along the slopes and accumulates at the valley floor. I think some of us know about the concept called as Mistral, or the winds called as Mistral, the drainage winds, where the winds accumulating here they are cold and they start moving along the river valley. So the valley bottom now becomes very cold compared to relatively higher heights. Now such type of inversion is the reason why this valley floor is not the preferred locations where people make their houses or have their accommodations. Most hill people prefer living along the slopes rather than in the heights or along the valley floor. So I hope you have understood what we mean by different type of inversions. Now quickly I will hint through and read some of the lines through your textbook. Again, this is climatology textbook by Savindra Singh, and it's always nice to read up something from the books. I have been repeatedly asked by my students and otherwise also, why should we read books? Can't we trust the notes? Notes and class jottings that you have, they are a form of writing, but they necessarily do not have all the concepts. Your reading without the textbook reading will always be incomplete. I mean, I firmly believe it is a disservice to discourage students from reading books. Yes, you don't have to read too many books. You don't have to read across shelves in a library. But you must have couple of standard books for reference. Books like this Savindra Singh series that we have, it is not to be read page by page, line by line and word by word. But there are sections you should read. Why? Because that gives you a sense of completion and you have something to refer from when you have doubts. So I stand by my word here. No matter whether you have done the classes or not, the textbooks are indispensable. You already spend quite a bit of money across different needs that you have while preparation. Books are a good investment. So get hold of this textbook. Now come to page number 65, Inversion of Temperature. The first column, the first line, it says, as stated above, temperature decreases with increasing altitudes in the troposphere at an average rate of 6.5. I mentioned 6.4 or 6.5 centigrade per 1000 meters is called as normal lapse rate. But sometimes this normal trend of decrease of temperature with increasing height is reversed under special circumstances. That is, temperature increases upwards up to a few kilometers from the Earth's surface. This is called as negative lapse rate. Thus, the warm layer lies over the cold layer. So, when you have inversion, the lower layer is relatively cooler and the above layers are relatively warmer. So, warm air lies over the cold air. Look at the next section, same column, types of temperature inversion. So basically it has a list, non-advectional, advectional, mechanical. That's one way of classifying. You can go by this too. The same terms I have only rearranged. This is more or less the three broad. So under radiational, radiation is also a type of a ground inversion. Under radiation we also have ground inversion. So page 65, second column, the first point, ground surface inversion is also called as radiation inversion, occurs near the Earth's surface due to radiation mechanism. This is also called as non-advection inversion because it occurs in static atmospheric conditions characterized by no movement of air, whether horizontal or vertical. So this is a calm, stable air. This air is not disturbed. And the energy is being lost by radiation. The surface is losing by radiation, cooling the surface and also the air near or in contact with it. Such inversion normally occurs during long, cold winter nights in snow-covered regions of mid-latitudes and high latitudes. In fact, surface inversion is caused due to excessive nocturnal cooling, nighttime. In the nighttime, there is no sun. And in the polar regions, high latitudes, the atmosphere is also rarefied. It's not very thick. And this is also true for deserts. There are no clouds to block the radiations that the surface is losing. So long winter nights are nocturnal phenomena, which means a phenomena of the night. Okay, so in fact, surface inversion is caused due to excessive nocturnal cooling of the ground surface due to rapid loss of heat from the ground through outgoing long wave terrestrial radiation. And look at the last 3 lines of this paragraph. Consequently, temperature inversion develops because of cold air layer below and the warm air layer above. What are the conditions? Is it listed down 5 or 6 conditions? It says long winter nights, cloudless and clear skies, presence of dry air. Because see, if there is moisture in the lower air, the lower air then can trap some amount of outgoing radiations. Because water vapor is a good greenhouse gas. But dry air, no clouds, okay, thin rarefied atmosphere, night time, no mixing of air. Okay, so all of this results in the ground losing the heat very rapidly. So this can be a good short note, the conditions, or even a multiple choice question in your geography prelims. Okay, so that explains. Page number 66 has the curve, the one that I drew here, where it shows that there's a kink, a bend in the normal lapse rate. So if we move on, the first column, last paragraph, upper air inversion. There are 2 types, thermal upper air inversion, and number 2 is mechanical upper air inversion. The thermal upper air inversion is the stratospheric inversion because of the ozone layer. It says so. It says the thermal upper air inversion is caused by presence of ozone layer lying between 50 and 35 stratosphere. The ozone absorbs the most of the ultraviolet. So as the energy comes in, the ozone layer traps the radiations and this layer becomes warmer. So understand this. Then look at the same paragraph, last line. It says the mechanical inversion of temperature is caused at higher heights in the atmosphere due to subsidence of air and turbulence convective mechanism. Both the reasons. When the air is rapidly sinking, I had drawn the diagram but rubbed that off, so I am repeating that for you. So when we have upper air subsidence, when the air above is sinking, this is the surface, the upper troposphere, air is sinking here. This is a zone of high pressure. And this sinking, this air starts warming up. Okay, because sinking, adiabatic compression and warming. And this sinking along with the surface in the winters, which is relatively cooler than this one. Okay, so it says because of subsidence of air, such inversion occurs in numbers of ways. Sometimes, warm air is suddenly transported. I explained the other one. The surface here and the warm air, because of turbulence, suddenly thrown above. So warm air is thrown above, that's one, and this sinking is another one. The sinking is mentioned. Look at the same column, page 65. I am reading the 7th, 8th line. It says B. The descending air is warmed by dry adiabatic rate of 10 centigrade per 1000 meters because of compression. This situation causes the existence of warm air above the cold air. Now this is an important one. Such mechanical inversion caused by subsidence of air currents is generally associated with anticyclonic conditions. Such inversion of temperature is very common occurrence in the middle latitudes where high pressure are characterized by sinking air. And this is also true for poleward regions of trade winds. And the trade wind tropical areas towards the poles, basically talking about subtropical high pressure belts. 30 degree latitudes. In the subtropical high pressure, which also is called as the poleward limit of the trade winds, we have the same thing. And this type of inversion is also called as Tradewind Inversion. Characterized by the poleward regions of trade winds are also characterized by high pressure caused by subsidence of air, and thus there is also frequent mechanical inversion of temperature. Next page, page 67, look at the first paragraph. The temperature inversion in poleward regions of trade wind is also called as Tradewind Inversion. And it explains why it happens. So I hope you have got the sense of what is subsidence mechanical. The other type of mechanical is the convective or the turbulent mechanical, where under hot conditions or warm conditions, the surface warm air gets thrown above. Okay, when it goes thrown above, there is warm air accumulating in the higher heights compared to relatively cooler air below. Why? Because the warm has been thrown up and there's some relatively cooler air which is not yet warm. It will take time to get warm and get thrown up. Okay, so even that is an example of mechanical inversion. Explain this to you. In advection, I believe I've got no problem. You can look at the diagram on page 67. 67, it shows the curve, the valley profile. The solid lines is the sinking air. The sinking air happens, I'm looking at the air, okay, near the surface. The descending air is a feature of the night time. Okay, in the night time, the mountain heights become far more cooler and the air starts descending. So I'm reading this out, page 67. Valley inversion generally occurs in the mountainous valleys due to radiation and vertical movement of air. This is also called as vertical advection inversion of temperature. The temperature in the upper parts of the valleys in the mountainous areas become exceedingly low during winter nights, because of rapid loss of heat from the surface. Consequently, they are coming in contact with the cool surface also cool. So as the surface becomes cold, the air is cold and this air is heavy and starts getting pushed down, accumulating here. Look at the last 6 lines of the same paragraph. Thus the air remains warmer than the air aloft, and hence the warm and the light air of the valley floor is pushed up. So as the cold air is sinking down, the warm air gets pushed up. Okay, so we ultimately have cold air accumulating along the valley floor. So that is the concept with the mechanism. And what are the consequences? Now this is the main concept. In inversion, there is no vertical movement of air. In inversion, there is stability. In inversion, cold air sinks and accumulates. And the cold air sinks and accumulates, it does not allow for a good circulation. So the cold air sinking, accumulating can trap dust, can trap pollutants, can trap dust particles and particulate matters, aerosols. This can increase pollution. This can increase fogs, because even the water vapor, ultimately whatever it must have been there in the air, also condenses here, cold air condensing. You'll have fogs here, and this is typical of the urban type of climate. So this conditions ultimately creates what's called as urban heat dome, where the inversion layer kind of traps everything inside it, doesn't allow for the circulation in the urban regions. So you have some points in page 68. Significance of inversion. It has not gone towards pollution discussion, but you can add so. Urban smog is a big issue related to inversion. So I hope you understand the concept. What is inversion? What are the types of inversion with diagrams? Where do we have it? That's the important discussion in geography. Where do we have these type of inversions and under what circumstances? Winter or summer or daytime or nighttime, clouds or no clouds, and moisture or no moisture. What are the conditions? And finally, what are the consequences? So any discussions you have about urban pollution, urban heat island, urban heat dome, please do have some reference to inversion issues. So I hope you understand this. Continue with your short jottings and your class answer writing. Thank you so much.